Hello, this is Josh Parisi. Today we are going to examine pipes that are flowing in a network. So, this video is going to be split up into two parts. So part one, which is this video, is going to create functions to calculate head drop and flow rate through a pipe. So in a single pipe segment, we're going to calculate head drop, change in head, and how to calculate Q, or flow rate. So, on the right-hand side of my screen is our pipe network. Be relevant in part two of this video, but I'm putting it up here to show you what our ultimate goal is. So, to create a pipe network code, first thing we have to do is we have to start out and create a function for head drop and flow rate. So, to create this function, what we have to do is we have to import. First thing we do is we import the programs we need. So we're going to import NumPy, which is the Python program that we use to essentially do math and run other functions like arrays, which will be very useful. So once you run that, we can then define our first function, which we're going to use. So when we're calculating for head drop, we need to know something called a friction factor. Now this friction factor, we're going to use what's called a Churchill function. So we're going to define F, friction factor, Churchill, and the two variables we're going to need to be defined for this function is our Reynolds number and our internal roughness of the pipe. So a Churchill function requires two smaller functions that we're going to call A and B. So our A function is going to look like, it's going to look like 2.457 times, and we're going to import a logarithm from NumPy. And we're going to, inside the log is going to be 1 divided by 7 divided by our Reynolds number. To the power of 0.9 plus 0.27 times, 0.27 times our internal roughness. And all of that is going to be raised to the power of 16. Now this function, or this Churchill function, is used for both laminar and turbulent flow, which is good for us so that we don't have to use different functions based on the Reynolds number. So this will just allow us to use the same function whether it is laminar or turbulent flow. So our B function is going to be 37,530 divided by our calculated Reynolds number. And then we are going to return two times 8 over our Reynolds number the power of 12 plus 1 divided by our a function plus our b function to the power of 1.5. And all of that is going to be raised to the power of 1/12. So this is our Churchill function. And like I said before, we use it to find our friction factor for laminar and turbulent flow given a Reynolds number and internal pipe roughness. So we'll run this to make sure we don't have any syntax errors, and it looks like we're good. So we're going to add a new text block, and we're going to call this one our D head. So we're going to use this function to calculate our drop in head as things flow through it. So for this function, we need Q, our flow rate, L, the length of the pipe, K, a constant that represents valves and other extra stuff that's involved with the pipe, D is the diameter of the pipe, and ED is the internal roughness of the pipe. So to calculate for our delta head, we need a few things. First thing we need is our flow rate, and what this equation is going to look like. It's going to be negative Q, negative flow rate, times K plus 4 times our friction factor, times the length of the pipe, divided by the diameter of the pipe, times our velocity squared over 2, all over G. So we have Q, flow rate, L, length, K, our constant, D, our diameter, and ED, our internal roughness. Those are going to be inputs into this function. So the first thing we need to calculate on our own is going to be velocity. So we're going to call that little v is going to be equal to our flow rate divided by we're going to use a pi times diameter divided by mu. Excuse me. Pi times diameter raised to the power of 2 divided by 4. So all this says is our flow rate divided by our area. So pi d squared over 4 is just the area of a circle. In this case, the cross-sectional area of our circular pipe as it goes through. And then another thing we're going to need our Reynolds number, because in order to use this function up here that we made earlier, we need our Reynolds number. So we have to calculate that. So Reynolds number is a relatively simple equation that is going to be equal to rho v d over mu. So rho is our density of our fluid, in this case air. V is our velocity, d is our diameter of the pipe, and mu is the viscosity. So viscosity is defined as the resistance to flow. So we are going to put all those ones in as variables, as shown here. So when we do this problem, when we apply it to this pipe system, we will define rho and mu for the gas that we're going to be using. So for this function, we're going to leave them as variables that will be defined elsewhere. Okay? And then once we have our velocity and our Reynolds number, we can finally calculate for our change in head. So according to our equation for head drop, we're going to have negative Q, which we're going to show by negative numpy sine Q to make sure that negative gets there. And then we're going to multiply this Q value times our K value, so our constant, plus 4 times our friction term, which we defined up here with our Churchill function. So it's going to be 4 times F underscore Churchill. And then we can put our Reynolds number and our internal roughness coefficient in here, just like we have up here. And that way we'll get the right answers as this returns. And then we're going to multiply this frictional factor by the length of the pipe and divide it all by the diameter of the pipe. So, and then multiplying that term by our calculated velocity, so multiplying that by velocity squared, divided by 2. This gives us our, I almost forgot the G. So this will give us our drop in head over the length of a pipe. So now that we have our function for calculating the drop of head over a pipe, we're now going to create a function for the flow through a pipe. So I made an error earlier. I kept referring to this function here as a drop-in, or as a delta head. That was not correct. What I meant to say was drop-in head, because a delta head we're going to use now to find flow, and that takes one head, compares it to another, so head in minus head out, and we use that to calculate for flow. However, using this function only calculates our head for one pipe. So, sorry about that little terminology. What I meant was drop in head. So, for this function, our flow function, we're going to need delta head, our change in head from one end of the pipe to the other. So we're going to call that just delta head. And that'll have to come from this variable will come from other sources, just like our L, K, D, and ED variables. So in addition to our delta head, we're also going to need the length of the pipe, our K constant, our diameter of the pipe, and our internal roughness of the pipe. So first thing we're going to do is we're going to take our delta head and make it positive, because we're going to need it to be positive later on. And I will point it out what I mean when we get there. So we're going to use our absolute value function from NumPy. NumPy.absolute value of our delta head. And this will ensure that this delta head value is positive. So just make this capital to make sure we know what we're talking about. And now we're going to add another little functionality where if this absolute delta head function, if this absolute delta head value, if this value is less than if it's less than 1 billionth, we're just going to set it to 0. That way, if we get exceedingly small numbers, we can round it to 0 to make our lives a little bit easier and our computer work a little bit less. So, now what we're going to do is the problem with our flow is that calculating flow, we need to know our frictional factor. Our frictional factor here, Churchill. And we also need to know the head at either end of the pipe. However, the problem that we run into is that we need our flow rate to calculate for head, but we don't know the flow rate. So what we're going to do is we're going to guess. We're just going to guess our flow rate. And the way we do that is we're just going to guess a friction factor. So we're going to guess that our friction factor F is equal to 0.01. So we're going to guess that the output of this function is going to be about 0.01. And the reason why we do that is so that we can get it down to one unknown that we can calculate for. So we're going to do our Q guess, our flow guess. It's going to be, numpy.pi. You have to import that pi variable from NumPy, times the diameter of the pipe, to the power of 2 over 4. So this right here is our area of the pipe. That'll give us the area of the pipe. And we're going to multiply that by our delta head times, we're going to multiply that by our change in head, and we're going to extract out kind of like our velocity value. So the way we get our velocity, because remember, volumetric flow is just our cross-sectional area times the velocity flowing through it. So the way we get out our velocity is by multiplying our head value, our change in head, times a gravitational constant, divided by our K constant, times our frictional factor, F, which we're guessing is 0.01, times our length divided by our diameter of the pipe. So, typing all that out is we're going to have our velocity. Keep in mind, when in the head function, our velocity is squared. So to get it by itself, we have to take the square root of the rest of the equation. So we got numpy square root of ABS underscore delta head. Oh, excuse me. Let's get that variable right. ABS delta head times 2 times g, gravitational constant, divided by the quantity of k plus 4 times our frictional factor, which we are guessing is around 0.01. We're going to multiply that by the length, divide that by the diameter. So, now that we have this, what we're going to do is we're going to run it to make sure we don't have any obvious syntax errors. So, looks like we're good. So, what we have here is we have just a function that essentially takes our delta head and we guess our friction factor and we run it. Now, this is going to be our flow for our guessed friction factor. Problem is, that's probably not completely correct. So what we're going to do is we're going to create another function, call it f to 0. And what we're going to do is we're going to calculate the head of the guess and subtract it by the actual delta head. So what that's going to look like is we're going to pull the function we created a minute ago, and we're going to put in our Q, so we're going to put in our flow rate, length, K constant, diameter, and internal roughness, all of the inputs required here. So we're going to put in all those. We get L, K, D, and ED from our problem that we're running, and Q is going to be pulled from whatever we put in here. So what we're going to do is we're going to then subtract this by our actual delta head, which we're going to get from this function. So ABS delta head and what this will do is if we can get our flow rate and our delta head to be equal to our actual delta head that we pulled from the problem, that means that our F, our frictional factor, and our Q is correct. So, now that we have that function, what we're going to do is we are going to basically run another function which will basically solve this problem for us. Get an answer where we find a head and a flow rate that's going to be equal to our actual delta head. So, in order to do this, we're going to need a Newton function. So we have to go back up here and import that. So we get that from skippy.optimize. Excuse my spelling. Skippy.optimize, we're going to import our Newton function. So running that again, we're going to run all these. And then we're going to pull our Newton. And we're going to have our f to 0 function. And if we look up here, this gives us a little blurb about what we need. So what we're going to do, what this allows us to do, is to find the 0 of our function. So our function is going to be f to 0, given a starting point, x of 0. So our starting point is going to be our guess from earlier, which is going to be good for us. And then you can see all these other optional arguments covered by this. Sorry about that. But we don't really need anything other than our function and our starting point. So our starting point is going to be our qguess variable from earlier. Okay. So now that we have that, we'll just call this variable results. Now that we have this, what we can then do is return a value for this flow. So we still need to finish this function. So we're going to do So we're going to return our delta head from earlier. This time we're going to leave its sign alone, because the sign, so we removed the sign up here to make these calculations a lot easier. But we're going to put the back of the sign here because the sign tells us which way is the fluid flowing. So for example, from here, we could say that this pipe from node 1 to node 2, we're assuming it's flowing from 1 to 2. However, if we calculate here and get a negative sign, that means we were wrong in that assumption, and that's actually going from 2 to 1. So that's what the negative sign is. And we just removed it to make our calculations easier. So we're going to multiply that delta head times our flow rate. Or multiply our delta head times our times the result of this function, which will give us our friction factor and our flow rate. So, knowing that, we're going to run that over. All right, no syntax errors. So, these are the functions that we're going to need in order to solve this. So these functions were created for just one pipe, but we are going to extrapolate them in part 2 of this. In part 2, so the next video, which will be linked in the description, to solve for the flows from each of these pipes. So, join me next time when we continue from this point in our code and go to finish the rest of our code. So, thank you all for joining me, and I will see you in part 2.